All right, let's get right into it. Today, we're going to learn how to decode the universal language of electronics. Schematics. They're basically the treasure maps for every circuit out there. And trust me, by the end of this, you'll know exactly how to read them. So, have you ever opened up some gadget and just stared at the circuit board? Or maybe looked up its diagram online and felt, well, completely lost? It can look incredibly complicated, right? Almost a little intimidating. Yeah, if you don't know what you're looking at, it's just a crazy jumble of lines, squiggles, and weird symbols. It absolutely feels like a secret code. And you know what? In a way, it is. It's the hidden blueprint of our entire electronic world. But here's the thing you gotta remember. It's not random chaos. It's a language. A language with its own alphabet, its own vocabulary, and its own grammar. And today, we're going to make you fluent. So let's get started. Okay, so every language starts with the basics, right? The ABCs. For us, right now, our alphabet is the set of symbols for the most basic electronic components. Once you get these down, you are well on your way. First up, we've got the resistor. This is probably the one you'll see more than any other. Its whole job is to resist, or kind of slow down, the flow of electricity. Think of it like a bottleneck you'd use to control traffic flow. And its symbol? It's just that classic zigzag line. Super simple, right? Next up is the capacitor. This little guy acts like a tiny, super fast battery. It stores up electrical energy and then can release it in a flash when the circuit needs it. Now pay attention to the symbol here. See that curved line? That tells you it's a polarized capacitor, which means it matters which way you plug it in. That curve, that's your negative side. And here we have this loopy, spring-looking thing. That's an inductor. Just like a capacitor, it stores energy, but it does it in a totally different way. It uses a magnetic field. You see these a lot in things like power supplies or audio filters. This one's pretty easy to guess, I think. A switch does, well, exactly what a light switch on your wall does. It either connects a circuit or disconnects it, on or off. The symbol even looks like a little drawbridge that can open or close the path for electricity. Of course, none of this works without some juice. You'll see a few different symbols for power. That stack of long and short lines, that's a battery. You'll also see symbols for DC, or direct current, and AC, alternating current. And that symbol that looks like a little downward arrow or rake, that's ground. Think of it as the 0-volt baseline for the entire circuit. Okay, so we've got our letters down. Now it's time to build up our vocabulary. Let's meet some of the more advanced components. These are the real workhorses that do some of the most powerful jobs in a circuit. This symbol here is for a diode, which is basically the one-way street of electronics. It lets electricity flow through in the direction of the arrow, but slams the door shut if it tries to go the other way. And a super common type you already know is the LED, a light-emitting diode. It does the same job, but as a cool bonus, it lights up when current flows through it. Now let's talk about the transistor. This is the absolute foundation of all modern electronics. It's an electric switch or an amplifier. You've got two main flavors, NPN and PNP. And honestly, the only difference in the symbol is which way that little arrow points. Here's a great way to remember it. For the NPN type, the arrow is not pointing in. So of course, the PNP points in. Easy. All right, these are the brains of the whole operation. Integrated circuits, or ICs. These are entire, incredibly complex circuits. We're talking millions, sometimes billions of transistors, all crammed into one tiny black chip. Because they do so many different things, their symbol is usually just a plain rectangle with a bunch of numbered pins sticking out. So to keep all this from becoming a huge mess, every single component on a schematic gets its own unique name. It's usually a letter to show what it is, like R for resistor, or C for capacitor, followed by a number. So you have R1, R2, C1, and so on. Yes, some letters are a little weird, like Q for a transistor or U for an integrated circuit, but those are just standard conventions you'll get the hang of really fast. So, we've got our letters and our words. Now we need grammar. We need to know how to connect all these symbols to make a sentence that actually means something, or in our world, a circuit that actually works. Okay, so all those lines you see connecting everything, those are called nets. The easiest way to think about a net is that it's just one continuous wire. It doesn't matter how it twists or turns on the page, every single point on that line is electrically connected to every other point on that line. Now listen up, because this is one of the most important rules. When you see two lines cross on a schematic, you have to know if they're actually connected or just passing by. If you see a solid dot where they cross, that's a connection. We call that a node. If two lines cross and there's no dot, they are not connected. It's like a freeway overpass. So the most important thing is watch for the dot. You can imagine that on a really complex circuit, drawing lines for every single connection would just look like a bowl of spaghetti. It would be impossible to read. So to keep things clean, designers often just give the nets a name. Any 2 points on the schematic with the same label, like GND for ground or VCC for power, are connected, period, even if there's no visible line drawn between them. Okay, we can read the map, we know what the symbols mean and how they're connected. But to really understand what's going on, we need to know a little bit about the physics, the basic rules of the road that tell us how electricity is going to behave in these circuits. And this right here is the big one, Ohm's law, V equals I times R. The absolute best way to get this is with the old water pipe analogy. Just imagine voltage, or V, is the water pressure. Current, I, is how much water is actually flowing. And resistance, R, is how narrow the pipe is, squeezing that flow. This one simple equation is behind almost everything in electronics. Next up is something called Kirchhoff's voltage law, or KVL. It sounds way more complicated than it is. Really, it's just about the conservation of energy. All it means is that if you follow any complete circle or loop in a circuit, all the voltage you start with from the power source has to get used up by the components along the way. You can't just lose it. And the last law for today is Kirchhoff's current law, KCL. This one is all about those nodes we talked about, the connection points, and it's super simple. Whatever amount of current flows into a node has to be the exact same amount that flows out. Nothing just disappears. Think of it like water pipes again. The water that flows in has to flow out. And that's it. You've just learned a whole new language. You can now look at a schematic, recognize what the parts are, see how they're wired together, and you even get the basic physics that makes the whole thing work. You can literally read the blueprints of our modern world now. You know, this knowledge is a genuine superpower. It's the key to fixing your own gadgets, inventing new devices, and really understanding the tech that's all around us. The map is now officially in your hands. So I've only got one question left for you. What are you going to build first?